Sorry for this inconvenience, for this technical hiccup. So basically, the story I'm going to tell you is a story about multimodality in language, which is, I think, a fairly neglected issue when it comes especially to human language processing strategies tackled from a computational linguistic perspective. So basically, what I would like to do today is to urge you to embrace the multimodality perspective in inquiring language from a computational linguistic point of view, because I think there are plenty of data there needed to be explored. They're waiting for us to analyze them. And because I think we can gain both fresh and old insights into the basic cognitive mechanisms underpinning language processing strategies by looking at this data. And to give you an example, I will focus on reading, which is an inherently multisensory activity, which is something that, how can I get, okay, here, I think, which is an interesting problem and an interesting task to learn, from the perspective of a child, because in order to learn to read, a child needs to integrate three emerging information flows. One is the word's acoustic image. The second one is the word's visual image. And we are introducing a third one, the tactile exploration of the spatial dimension taken by each word in a written text through finger pointing. Well, finger pointing reading is a typical way of learn to read, which is a practice fairly established in our schooling system, for example. We invite the child, while the child is reading, to finger point the text and the single words. So in this way, you can get, a kind of visual and tactile experience of the kind of words he's reading or she's reading. So investigating the multimodal nature of reading can provide new and old insights. And I insist also old insights, because I think the kind of evidence I'm showing today is kind of reassuring from a linguistic point of view. In order to capture all these kind of signals, we establish a kind of infrastructure, which we are sharing with several groups who are working with us. But I'm not focusing on this infrastructure because some of the features of this infrastructure, the way we capture tactile data about finger pointing reading, will be illustrated by the next talk, after my talk. So I will not talk about finger reading, but I will focus on the difference between eye tracking evidence and the vocalization of the words while we are reading them aloud. Okay, so basically the signal is the one that appears here on the top half of this screen. So we see the signals as we projected along two scales. We have the horizontal axis, which represents time, and the vertical axis, which represents the position of each letter in the text. Okay, the ordinal position of each letter in the text. And we project the signal that we capture through eye tracking evidence as red dots in the top half, while the green dots represent the evolution of the vocalization, basically the audio recording of the file, the text being read. Okay, so the green dots are the vocal recording of the text being read, while the red dots are the fixation points of the eye, which is going through the text while reading, okay? So you can see that the eye does not explore in a continuous way the space defined by the written text, because the eye goes by fixating a single word and then jumping to the next word. So there is a jump, a discontinuity there. It doesn't go through all the characters making up a word, but just fixate one particular character, and then it can explore, the neighborhood of that particular character, and then fixate the whole word, and then jump to the next one, or even the word after the next one, because the eye can skip some words, for example, short words or grammatical words while reading. So this is the typical trajectory that is followed by the signal. I would like us to focus some kind of empirical evidence, which is represented, for example, by saccades. Saccades are jumps either forward or backward, as in this case. So the eye in this case is jumping from one word to the immediately preceding word. And fixation is represented by this kind of red segment, which is the time spent by the eye in fixating a particular word. And then you can see also there are some other intervals represented by voice breaks here. This lack of green dots there means that the voice is making a pause, okay? is pausing between pronouncing one word and the ensuing one. But we will focus especially on this effect. EVS means eye-voice span, which is the time distance measured between the time we fixate a particular word. Remember this notion because it will be important across our talk. The time we fixate a word and the time we start pronouncing that word, vocalizing that word. This is not a kind of, this kind of event is not contextual, it's not concurrent, especially in fluent readers. We first fixate a word, and then after a few words, we start vocalizing that word, okay? And this time span is called the eye-voice span. It can be measured in terms of times, centiseconds or milliseconds, but it can also be measured in terms of space. Here we are measuring the distance between the eye and the voice along the vertical dimension, means along the dimension defined by the letters printed on the page, okay? And these are two complementary dimensions. So what we see here is that the eye-voice span is a kind of prominent effect in the way we read a text as adults, okay? We can see the progression of the eye-voice span. This is a kind of ascending, a kind of line going up as we go through different readers at different grade levels, a different age of schooling, okay? 13 ages, the younger one, younger adults, up to PhD students, PhD actually postdoc, 21 years of schooling, okay? And we see this effect, although they are all mature readers, they tend to widen their eye-voice span, which basically means that as soon as you become more skillful in your reading practices, you tend to widen up this kind of eye-voice span. So you tend to delay the articulation of a word with respect to the point in time where you started fixating that word, okay? So you remember that in terms of time, and also in terms of space, which is indicated in the other graph, in the other box plot at the bottom of the screen, you tend to increase your span as soon as you become a more proficient reader, okay? And this is something that we like to inquire also in the process of learning how to read. So there are several interpretations, possible interpretations. So this is a kind of schematic representation of what I mean, by eye-voice span in terms of space. Here we are measuring the distance in terms of characters. So we are fixating the first word in this kind of many funny episodes. I split the sentence in this phrase into syllables, orthographic syllables. And then you can see that the voice is pronouncing many, the first syllable in many, while the eye is fixating the ensuing word, funny, okay? There is this lag. And in this case, the lag is of about 6 characters. This is the way we measure things. So when you think of the eye-voice span, you have to think of this kind of space lag between what the voice is doing and where the eye is looking at, okay? 6 characters in a kind of lexical way of reading words, okay? This is a kind of lexical strategy. We are pronouncing the first way, but we are fixating the second way. So in this style of reading, I will read something like many funny episodes, okay? Because while at the time I'm vocalizing the first word, I'm still fixating the second word. So I will introduce a kind of voice break between the first word and the second word being read, okay? There are different interpretation of this effect. For example, the most authoritative one is done in a paper by Laubrock and Kligel in 2015, and they say that proficient readers can parse written words visually more quickly than they can articulate them, okay? That's the logic behind this. So already fixated words are then stacked in a reader's phonological buffer waiting to be vocalized. And this means that we can set an upper limit of EVS, and this is given by the capacity of a reader's phonological buffer. So the larger is our buffer, the larger the span, the e-voice span, between the time I start fixating and visually read that particular word at the time I start vocalizing it, okay? So that's the story, the phonological memory buffer. I don't know if you're familiar with this literature about working memory, but basically we can stack several words and then we can start articulate them. And the larger the span in terms of our phonological buffer capacity, the larger the capacity of our memory buffer, the longer the span. Okay? And this is done because the I is quicker than the voice. That's the story. There is another story. Okay, the effect of this, for example, experimentally, is that when EVS gets too large, when the I is too far ahead of the voice, the I slows down, okay? Because it has to wait for the voice to catch up, to go through the buffer. That's the story. It's a very simple story, but it's effective in describing this phenomenon, okay? But not as effective as, well, we'll see. And we have evidence here that this effect really exists, that the I slows down when the span gets too large, okay? I won't spend too much time on this. There is another interpretation, which is more kind of telic interpretation. So what for? Okay, we do that because we have a phonological buffer of limited capacity. And the wider the buffer, the longer the span. But why? Why on earth we have to do that? Why on earth we have to coordinate the I and the voice in such a complex way? Okay? Well, the answer is that we do that because we are fast readers, because we want to be fast readers. And since the I can go faster than the voice, we can let the I go ahead of the test so that we are ready to articulate words because we have already fixated the words before we articulate them. So this gives us continuity to our way of reading. Instead of reading something like many funny episodes, I can do something very quickly. Many funny episodes, okay? Many funny episodes. I don't have to put breaks between words because I've already taken advantage of the fact that my eyes is going through the test more quickly than the voice, okay? So basically, we do that because this is more efficient. And we calculated this effect. And this turns out in our data to be true. I'm not going to explain these graphs because, I'm a bit delayed. So we'll skip the evidence. But believe me, we found evidence that this is true. Fast readers actually have this kind of effects and slow down more often than slow readers because their eye goes quicker. And because their reading rate is quicker, okay? But this is not the end of the story. So this is where, so far I've talked about in terms of cognitive mechanisms, which are completely far away, completely independent of issues of the linguistic structure of the text, okay? I've reasoned in terms of cognitive mechanisms underpinning reading. I've not talked about, for example, the complexity of the text. Nothing in linguistic terms entered this picture so far. But this is not what really happens. Because, if efficient readers will maximize the EVS, the story that I told you so far, we should find the same kind of EVS across the text, no matter what we read. Okay, we should always maximize because we tend to be fast readers. So the span and the length of the span should be independent of the structure of the text. Okay, but this is not the case. Actually, in reading a text, we modulate our span in a kind of very elastic and flexible way. And it turned out that the intra-reader variance of the I-voice span, so the variability of the span within the same reader, is much larger than the variability of the span across readers. So the variance between my span and your span is much smaller than the variance of my own spans while I'm reading the same text. Okay? So this evidence clashes with the kind of reasoning I suggested so far. And in fact, if we try to correlate the speed or the rate of the voice with the time we spent in fixating the words, we find this kind of evidence. The correlation between the timing of the voice and the timing of the eye, in reading one particular word, is at the word level 0.36. Is a strong, significant correlation, but it's not that strong. But if we look at the same correlation at the level of chunks, which basically means at the level of non-recurrent phrases, the correlation goes up to 0.6. This is a strong correlation, okay? But if we go up at the level of sentence, the entire sentence that we read, the correlation gets even higher, is 0.9, okay? The correlation between the time we spent in fixating a word, fixating a sentence in this case, and in articulating that sentence. The correlation is very high. Means that the two signals do not synchronize very well at the word level. They synchronize better at the chunk level, but they synchronize nearly perfectly at the level of sentence, which means that the voice can catch up with the eye at the end of the sentence. So that means that the span tends to get narrower, to reduce itself at the end of linguistic structures. Okay? That must mean something. Okay? Okay, that is reminiscent of one evidence that I didn't talk about so far, that we can have different style of reading. For example, at the initial stages of reading between the second grade and the third grade, children start reading lexically. So one word at a time, word per word. So they go like in the top left corner of this slide, many funny episodes, okay? But this is not the way we read as adults, as proficient readers. Actually, we read at the level of chunks, and we say something like many funny episodes. And in fact, from a prosodic point of view, this is a much more natural way of reading, because it means two things. I can put stress on the final element of the chunk, the lexical head of the chunk, which is the most prominent one from the point of view of the linguistic structure, but also for my understanding of the text. I need to read the whole lot with the eye before I can provide the right sort of prosodic contour in reading the whole chunk. So for reading things naturally in a way that reflect my understanding of the content of the text, but also the prosodic structure of the text. So in order for me to read well, I have to read in a chunk-wise way, okay? I have to read something, many funny episodes, okay? And this means that the eye must fixate the last word of a chunk while I'm starting articulating the first word, okay? Have to be aware of the entire prosodic context I'm reading, okay? This is the key, of the story I'm going to tell you. So we find evidence for this, and we actually found that adult readers present this kind of profiles at the level of prosodic units of different sizes. Okay, we have this curve, as descending curves describe the reduction of the span while we are reading either a chunk, a syntactic chunk, or a weak prosodic unit, which means a piece of text followed by a comma, for example, or a strong prosodic unit, which means a sentence followed by a full stop, okay, where we make a long pause. So we tend to reduce this boundary, okay? And this is the evidence we plotted about. This is about adult reading, okay? But one interesting thing, and I think is pictured in this diagram, in this plot on the left, which shows that when we are reading a piece of text made up of 3 words, okay, the logic is that to start reading the first word, we have to wait for the last word to be fixated, okay? And that means that in reading a 3-word chunk, I have to expand my IV span longer than if I'm reading a 2-word chunks, because I have to wait for longer, okay? So the span will be longer in reading a 3-word chunk, less long in reading a 2-word chunk, and in reading a word chunk will be just a lexical, kind of, in terms of size, a kind of lexical span. And this is exactly what we found. And this is exactly what is plotted in the plots on the left. This evidence is tracked down both for the eye, okay, which is on the right-hand side, the brown kind of curves, also for the finger. And we show this to make the point that there is a strong correlation between the movement of the finger and the movement of the eye. So the movement of the finger in finger point reading reflects the behavior, to an extent reflects the behavior of the eye. Okay, and this graph on the right pictures what I'm talking about. So you have the fixation times spent by the eye, and then the voice has to wait until the eye fixate the second element of the chunk before he starts vocalizing the chunk. Okay, and this is shown for a two-word chunk on top and for a three-word chunk. And this kind of diagram explains, in a way, the kind of evidence I was showing in the plot on the left-hand side. Okay, explains why it is so. So this is the dynamic. But what about children? Okay, I think I already explained that. Well, this is what we call the adaptive reading hypothesis. Okay, EVS is not only an indicator of individual reading proficiency and working memory capacity, it also reflects an adaptive reading strategy, which is contingent on the structural features of a reading text. Readers have an elastic span, which stretches or strings far enough to read to language units of varying size. Typically, developing readers show a steady increase of the spatial eye voice and finger voice spans. Okay, but what about children? So this is the same box plot that I was showing for adults, which in this case is shown for children. And we have a mismatch between the evidence that I was showing for adults and the evidence for children, because the evidence we show for children is, in terms of time, we have a reduction in time as soon as we go from early readers, so from early graders to late graders, so like 5th graders. We have a reduction of the span in terms of time, okay? But we have an increase of the span in terms of space, in terms of the characters, which represent the advantage in terms of space of the eye with respect to the voice. Why it is so? Well, because the child is getting more and more fluent. So the time of preparation of the phonological representation corresponding to a written word and its vocalization is reduced. So in terms of time, we have effectively a reduction of the span between the eye and the voice. But in terms of the functional distance of the eye with respect to the voice, the span gets larger. So we have the same effect that we shown for the adults, also in the development of the child. We have a clear effect that the child is getting more proficient, and actually the child is moving from a kind of lexical way of reading to a chunk way of reading, okay? So it's going basically from syllables to words to chunks, okay? Now, I'm going to show you very quickly how much time is left? Sorry, is that one? What time I'm expected? Well, 5 minutes. I think I can afford 5 minutes. Okay. Okay. So I'm going to show you a few evidence attesting that the child is sensitive to linguistic units, to functional linguistic units for reading, not just letters or bigrams or, you know, more kind of distributional effects we are maybe more familiar with. But actually, the key point is that they are sensitive to linguistic units like syllables, for example, because syllables are functional to reading, actually. They are some kind of, you know, key prosodic units. And this is the effect, for example, between grade 2 and grade 4 and 5 children with respect to the frequency of the average frequency of one syllable within each word. So you can say that there is a clear effect of children of grade 2 speeding up if the syllabic structure of a word is more frequent, okay? So they are sensitive to this frequency, syllable frequency effects, while later children, you know, later graders are no longer affected by this effect. That means they have already memorized all types of syllables, you know, in their orthographic lexicon, irrespective of their frequency. They have already learned a large enough amount of evidence concerning syllables to be sensitive to frequency effects of syllables. And the same kind of differential sensitivity is found when we measure the frequency of bigram of syllables, okay? Two syllables in a row. I mean, you see that, you know, the time of reading, of fixating goes down as a function of the frequency of the two syllables making up a word, while later graders are no longer sensitive to this effect because they have been exposed to large enough evidence concerning reader. So syllables and bigram of syllables. Obviously, they are also sensitive to word tree effects. Oh, this is a kind of nice evidence. I don't know. I don't think I have time to explain it to you fully, but we can discuss it in the break. I mean, the sensitivity to the conditional probability of going through a word. So how predictable that word is from the point of view of the lexical experience of a child. All children, I mean, of all graders, are sensitive to this. I mean, easier words are words which are more easily predictable. And this is what that graph is. So all children of all grades are sensitive to this particular probability structure. And here it's the interesting part. How sensitive they are to chunk effects, chunk effects. This is the plot of the sensitivity of 2-token chunk, 3-token chunk, and 4-token chunk, okay? Obviously, this is the measure in terms not of fixation time, in terms of the EVS span. So the larger is the span, the older the child, the reading child, the more experienced is the reading child. As you can see, you have a diminishing effect of the EVS span at the end of the chunk in readers from grade 3 above, okay? You don't see this effect in grade 2 children. Okay, the curve is flat, it's completely flat. They are not sensitive to that effect at all, which means they can read lexically, but they cannot read chunk-wise. They cannot read longer stretches than just the lexical one. While later graders can. They can report those effects. Certainly for 3-token chunk, for 4-token chunk, it's difficult for them, okay? And this effect is no longer significant from a statistical point of view. But this is natural. This is what we would expect. Okay, these are other more classical effects on top, which is the word length effect. The longer the word, the longer the fixation time taken by the child. This is an effect more prominent for grade 2 children, less prominent for later graders, okay? And this, you have the word frequency effect, which is again more prominent for 2 grade children and less prominent for grade 4 and grade 5 children. What you can see in the 2 graphs below is that if we measure these statistics in terms of bigram of letters, which are not linguistic units, actually, they are just 2 adjacent letters in a word, you don't see any frequency effects, which means that children are sensitive to effects of syllabic units and beyond the level of syllable, also morphemes, because the word tree effect point to the morpheme, the morphemic structure of a word, but they're not sensitive to more abstract kind of distributional effects like, for example, bigram of letters or trigram of letters, which is, I think, a reassuring evidence for us as linguists, either computational or not. The fact that in carrying out the reading task, the child is sensitive to linguistic effects, to distributional effects that concern the linguistic structure of the text, is certainly reassuring. Okay, here is some literature about the various phases in the development. And these are matches, this kind of model, which is by Uta Frith, matches the kind of evidence I was showing to you. Although we showed, I think, interesting multimodal evidence that this is true. I mean, in the developing child. And this is the hypothesis of how this can happen. This is a model by David Shares about the self-teaching hypothesis. I don't know if you are familiar with this two-root way of reading. I mean, the phonological way is shown on the right-hand side of this graph, while the lexical way is shown on the left-hand side, which basically means that if we know a particular word already, we can recognize that as a whole word. So we go through the lexical path, okay? We recognize the whole word, we access the representation of that word in our orthographic lexicon, we retrieve the phonological representation and we read it. So it's a kind of holistic way of reading. a lexical way, if you like it. While the other one is the phonological way. We read a word syllable by syllable, and then we blend this kind of sounds, and we obtain the whole reading. But this is slower. This is less efficient. This is why the child tends to move from a syllabic stage of reading to a lexical way of reading, because it's more natural and it's more efficient. And this is also true of languages with transparent orthographic scripts, like, for example, Italian or Bulgarian, for that matter. They go, they assume to go through the phonological reading, but in fact, for efficiency reasons, they try to shift, as soon as they can, towards the lexical reading. Okay? In fact, I do not agree entirely on this kind of two-way route of conceptualizing the learning. In fact, we have self-learning architectures like recurrent neural networks that can collapse the two dimensions. So you don't need to have a separate way for the phonological coding and a lexical way. You can collapse the two dimensions just in one recurrent dynamic lexicon that develops lexical representation on the basis of chunking a few strings of words, And I have no time, of course, to illustrate this kind of more advanced neural network-based models. But this is, in words, the self-teaching hypothesis revisited. No need to postulate two separate components. One single recurrent mechanism can account for the incremental storage of longer and longer letter-to-sound sequences. Pronouncing shorter strings with no delay, chunking, is a precondition to be able to fluently pronounce longer strings. And languages with phonologically opaque script require storage of longer consistent chunks. So the difference between reading, for example, Italian and reading English is that you need longer chunks of letters in order to correct reading an English word compared with a Bulgarian or an Italian word, okay? But that's the only difference in the learning mechanism. You don't need to postulate two different ways of reading or two different styles of reading. You can just compress them into a single mechanism. Okay, that's the end of the story. So we showed that multimodal, I hope I showed, that multimodal language evidence provides invaluable information on readers' processing strategies. Okay, this info sheds light on general cognitive mechanism underpinning as a language skills, like, for example, the phonological buffer mechanism, the working memory mechanism. But we believe that also sheds light on the requirements of the specific language task at hand. Okay. And I think it's, at least for me, I hope you're going to share this view, that is a matter of intellectual gratification that these requirements make readers sensitive to genuine linguistic processing units. Okay, and that's about what I wanted to tell you. Thank you very much for your interest. This is obviously work carried out by the entire lab. It's not just my own work. Thank you for your attention.